Okay, so this next lesson, 8.3, oh yeah?
Nothing. I thought your mic was on.
Okay. This lesson is about constructing confidence intervals for a population mean. We've been working with proportions up until this point. What you'll notice is this section sort of split into two parts. The very first part is about constructing a confidence interval if you actually knew the population standard deviation, which is what's called a one sample Z interval for a population mean. But if you think about all these numbers, if I just took a sample from a population and all I have is the information from that sample, I do have X bar, I have the mean. I could calculate a Z star, the critical Z value, but I don't really have sigma. Because I took just a sample from this population, I don't have what you could think of as a census. I don't know everything about this population, so I don't have the sigma from the population. And so this, constructing a confidence interval this way, I think is just unrealistic. It's not something we ever really do, except there are cases where we will use this information, specifically the margin of error part, to think about what size sample would I need in order to create some kind of a confidence interval with a specific margin of error. If maybe I knew from previous studies that the standard deviation is supposed to be a certain number. So I have this information all on here, and your book spends a little bit of time doing confidence intervals, and they give you like a pretend sigma that's supposed to be the sigma for the population, but it really just doesn't make sense to do that ever, except for in one case, and that's what we're going to start with today, is how do you choose a sample size for a desired margin of error if you are estimating a mean. And so how we did that with proportions is going to be the same way we do it with means, except the formula is just slightly different. What you'll notice is we want a critical value Z star, and that's going to be depending on our confidence level, 95%, 90%. But then we have the standard error part of it, or the standard deviation of the statistic part of it, sigma divided by square root of our sample size, which we're not going to know, is less than or equal to some value that we want. Maybe we want our margin of error to always be within 3 percentage points. Or 3, in this case, because we're not talking about percent, because it's means, maybe within 3 inches, or 3/1000ths of an inch, or 3 centimeters, or 3 meters, or 2 something. Okay, that's what we want it to be within. What we're going to do here is based on, usually this number right here, our sigma, is going to be based on previous studies. So let's look at page 500, and you don't have to look at that if you don't want, just listen. It says, researchers would like to estimate the mean cholesterol level, mu, of a particular variety of monkey that is often used in laboratory experiments. They would like to have their estimate be within 1 milligram per deciliter of the true value of mu at 95% confidence level. A previous study involving this same variety of monkey suggests that the standard deviation of their cholesterol levels is about 5 milligrams per deciliter. And so what you'll notice is they've given us sigma from the population. They said that in previous studies, sigma is 5 milligrams per deciliter. They've also said that Z star is going to be based off of a 95% interval. Who remembers what our Z star value is for that 95%? 1 point, yes? Is that what you said, 1 point? It is 1.96, okay? You can use table A. Yep, so in table A, just remember that with the 95%, you're looking for 5% total in the two tails, so you're looking for 0.025. Did you do that wrong? So in your table, you have to be careful that your Z star is actually what would give you 0.025 as the probability below it in the table. Okay. So this side would be 0.025 as well. So with this, if you did look at table A, you find, do you want me to show that how to do that again, or you just, okay. So let's set this up. So it's 1.96 multiplied by our sigma divided by square root of n, which has to be less than or equal to, from this problem, they wanted to be within 1 milligram. I guess I don't need to put the units in it, just within 1. And so there's an easy and there's a hard way to solve this. Your book, if you're going to look at the example, does the hard way for some reason. But if you're looking at a fraction multiplied by a number, the easy way is you just multiply the top numbers together. 1.96 multiplied by 5, and then worry about the square root of n later. The reason that's easier is because at this point, now what I can do is multiply the square root of n out of the denominator to both sides. So something like that. Does this make sense so far, the algebra part of it? Okay. And then 1.96 times 5 is 9.8. And then 1 times square root of n is just square root of n. And then what do I do to get rid of the square root? Square it. So when I square the 9.8, I get 96.04. I didn't show the work there. And so we just say that n, the number of monkeys they need for their sample, has to be greater than 96.04. So we're actually going to say n has to be greater than or equal to 97 monkeys. It seems kind of picky to say round up with only a 0.04, but that's just generally what we want to do. We want to make sure we are not going the wrong way with it, because we definitely want to be the right direction. Okay, any questions on that? Okay. So what we're going to do on the next page is do another one kind of similar just to see if you can pull out the correct information. So it says example, but I'd like you to try this problem with about homework. I read it for you. It says administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate mu at the 90% confidence level with a margin of error of at most 30 minutes. Yeah. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. Remember, this is how many minutes they spend per week, so it's over the whole, it's not per day. How many students need to be surveyed in order to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30 minutes? So take a minute and figure out how would you set that up. Ask me questions if you're stuck. So Hasley, tell me what would we use for the Z star value? 1.645. So we'll do 1.645. Aaron, what did you put in here for your standard deviation? And then less than or equal to, what is our margin of error part, Alex, that we want it to be 30? And so if we multiply the 1.645 by the 154, we get 253.33. And then I'm going to multiply the square root of n over times the 30. I don't know why I put that first. 30 times the square root of n. At this point, because it's not a 1 times square root of n, what we should do is divide the 30 back to the other side before we square both sides. Does that make sense? Good? Aaron, are you okay with that? So then, when I take and divide 253.33 by 30, I get 8.444 less than or equal to square root of n. And then I'm going to square root that, or square that number. So I get 71.3 something. So we want n to be greater than or equal to 72 students. Yep. Okay, I multiplied the top numbers here together as if this was like a whole number times a fraction. And I multiplied those to get the 253. And then I multiplied the square root of n out to both sides as well. Does that make sense? So I think I skipped this step right here. From here, then I multiplied the square root of n to both sides to get this one. And then I divided by the 30 to get this. Is that good?